Morning. Well, at least it's morning right here where I'm at. Maybe afternoon, evening when you're actually viewing this recorded lecture. And we'll just get right started. We're in statistics, beginning statistics. We're in a chapter that we're comparing averages, at least between means. There is another section that I'm not covering that compares proportions. Your last section that we took a look at was comparing means, two data sets that were dependent upon each other. Something like if you took the same group of people and you asked them to take their resting pulse rates. So let's say you take 30 people and ask them to take their resting pulse rates before they do anything, and record those. And then you could take the average of those 30. And then you have all 30 of them jog in place for a minute, and then take their pulse rates right after and record those. Of course, you would expect that those pulses would be increased higher. And you take the average of those and you compare those two data sets. Now that's called dependent because it's the same group of people. This section is going to be called independent, where there are two separate groups of people. Therefore, the sample sizes for each group can be different. They can be the same, but they definitely can be different. And that's what we're going to take a look at today. So as you can see, possibility of the definition that I've written up here for you: unpaired data, independent. So they're not dependent upon somebody else. So boys and girls, a group of boys, a group of girls, smokers, non-smokers. So that gives you an idea. And you want to test the difference, see the difference via subtraction between the two populations. And you can see the population, the first one and the second one, the difference between those two. The distribution, I'm going to read through this, and I've worked out the main idea already for you. And so I'm going to step through it with you. And I know you can read it, but maybe it's helpful for me to highlight a few things. The distribution of the difference of two means, and they're going to call it D, lowercase d, is what I'm doing right now. And so if you suppose a random sample, size n sub 1. So this is like the first group, mu sub 1 and n sub 1. So suppose you take a random sample of size n sub 1. Of course, we want to make sure that they're all greater than or equal to 30, ideally, so that you could at least use what's called case 2. Case 2 is when n is greater than or equal to 30, so it's approximately normal. And highly unlikely that you have sigma, highly unlikely. So you're going to be drawing from the sample standard deviation from each group. So it sounds like it's going to be a t. And as you can see, there's a t down here. In addition, a simple sample, again, will be taken from another group. And same thing, you don't know what the true population of that group is, average, nor the standard deviation. So if the populations are normally distributed or approximately normal, then you've got this data value, which we will find this, somehow we'll find this with the calculator. It's not that intimidating if you think about, oh, it's plug and chug. You're going to get the X bars from your calculator, or just add them all up and divide by as many as you have. These guys right here, it's going to be given to you. Well, actually, you'll find that out. It's going to be given to you somehow, this part. Little s and little n's are all from your sample size. So it's just plugging it in and getting a number. Turns out that mu sub 1 minus mu sub 2 is equal to 0. And here's the reason that you'll see down below. Let's skip on down below. As you can remember, the hypothesis testing that we're taking a look at are in such a way that you've got not equal to, that's a two tail. You get a less than, and I've oftentimes said you just do the complement symbol, which is greater than equal to. The author will take equal to on here and there. So keep that in mind, equal to. Here, I'll even do it. The author does this, and it's very acceptable because ultimately all you're doing is you're rejecting or don't reject this, but you're talking about the alternate. So go ahead and change these to equal. It's not a big deal. So if you notice here on all these, the difference is equal to 0. That's what you are assuming to be true. Then you're assuming that the mu sub 1 is equal to mu sub 2. If I did the algebra and brought over mu sub 2, you'd get mu sub 1 minus mu sub 2 is equal, my mistake. You get mu sub 1 equals mu sub 2. And that's how the book starts off, by the way. The book starts off oftentimes if they say mu sub 1 minus mu sub 2, because that's called the difference anyway, comparing the means. You could say mu sub 1 equals mu sub 2 to start off with, and you could say the population here average is less than the population average here. So oftentimes you may get a statement where it talks about when you compare it, one's less than the other, and it probably makes sense. Well, think about it. Even the resting pulse rate, now that's dependent, but you're comparing the two. So you oftentimes will have one's bigger than the other, but you can move it to the left side of the inequality and have a 0 there. Look at this, watch. Go back to a couple of these, even way back in chapter 9. Way back in chapter 9 that we did. I'll even show this right here. Back in chapter, here's a different packet. Way back in chapter 9. I know, you're waiting for me. Think about this. Even right here. If all I have to do is move the 673 over to the left-hand side, and you have a 0 on the right-hand side. So it's just algebraically changing it to look a little bit. You go mu, subtract 673 has got to be less than 0. Whatever this is, the difference between that, which we don't know, and 673 has got to be less than 0. So this way that I'm writing, I think is the author's way, is how we're going to end up attacking this eventually. These guys right here. We'll keep that in mind. So in the formula, if you think about that, if this is equal to 0, see how it's equal to 0? Mu sub 1 minus mu sub 2. Mu sub 1 minus mu sub 2 is equal to 0. Put a 0 here, and then you've got this formula that simplifies down. So it's really not that big a deal to try to find the data value if you didn't use your calculator or there wasn't a calculator place to find that number. Okay, let's take a look over here, the worked out problem I have for you. So Professor Sullivan's students at What's the Matter U? Chuckle. What's the Matter U? University. Well, anyway, they felt that he was a tough grader than other speech teachers. Speech professors. Professor Sullivan was harder, and they decided to test this. And here's your alpha. So if you thought about 0.05, that's your alpha. So it's given. So 8 of them took a 2-hour shift. So 8 of the students that Professor Sullivan used to have took a 2-hour shift, and they assigned randomly at different times of the day, try to make this as random as possible, and days of the week, and the distributed questionnaire to each student on the basic main quad. And they felt this was a reasonable approximation to a random sample of current students. And they asked the students not to take a questionnaire if they had already submitted one, so not double dipping. The questionnaire asked whether the student had taken speech in a previous semester. Okay. If they said, yes, we did. And then they say, well, which professor did you take it from? And what was your letter grade? If they said, I did not, then they just put that aside. They're only looking at the sample of the ones that said, yes, I did. And then the question is, after that, well, which professor? So it's either Professor Sullivan or the other professors. We're just comparing Professor Sullivan against the others. It would be possible to do analysis with the categorical data of letter grades, but we're not going to do that. The student, they counted A as a 4-point, which is pretty typical with grade point average. A minuses, okay, the institution we're at here at Santa Rosa Junior College, if you're watching it and you're not from Santa Rosa Junior College, well, here at this institution, we do not have plus and minuses. It's only straight A's, B's, C's, and D's, and F's. But assuming at this institution, Professor Sullivan, A minus was 3.7 and so on. So they have performed the analysis, meaning not analysis, but the calculations. They performed the calculation. They took 32 Sullivan responders and say, yeah, I took Sullivan. And their results, they found out that the average, grade point average was, for those letter grades, was 2.21 and a standard deviation of 1.44. All the other professors, which 54 of them, so it looks like about a third have taken the ones they sampled that said, yes, I took speech. About a third, actually a little more than half have said, yes, Sullivan. Even though people had heard that he was a tough grader, you'd think that they would have gone with a different grader as a student's perspective. Anyway, these are the results. So if you look, hey, GPA for the letter grade looks higher than Sullivan. Sullivan's lower. So it does look like, apparently, or it seems to be, with the sample of what, 86 that said, yeah, they took speech last semester, that Sullivan is harder. It does seem that way. But we want to make sure that, statistically speaking, with an error or a alpha being 0.05, we could agree with that wholeheartedly. So in this test, we have unpaired data, and they're numeric. So they're not categorical, they're numeric. So I guess we call that quantitative, right? Quantitative data. The requirements for each sample are the same as the test for the sample in a one sample t-test, meaning you're going to make sure that both samples are approximately normal. So it's true, 32, 54 is going to be a T, and they're random. So we did something, and they might have done systematic that we learned about, and they've got to be independent of each other. So there's no person saying, well, I took two professors. I took Sullivan and I took so-and-so. No, you only want a completion of the class with one grade with one of the instructors. So there's no overlap. So we'll just go with Sullivan's is number 1 and the non-Sullivan is number 2, sample size number 2 of the population. So Sullivan is here and the others are number 2. So if you look at here, MUSE of 1 less than MUSE of 2, Sullivan's GPA is less than or lower than the others. And notice how it's equal rather than greater than equal to. And we want to make sure everything's good, which we have already. And all the information is given to you. Here's the information from the table from the left. There's going to be a place in the calculator. Your author in our textbook briefly identifies or talks about what is pooled mean. I am not addressing that here in this course. And so therefore, and it's not going to apply for us for any of our problems we're going to do in this course. So on your calculator, make sure you choose not pooled in your calculator. So at the end, this is the data value right here. This is somehow we're going to get everything out of the calculator, and look at, you can see this right here. So the data value, where is the data value? Right here. Okay, these are all the results here. Oh, here it is right here. Check. Okay, wrote those down. P-value. Okay, check. Got that. Now, degrees of freedom, the calculator does a much more precise degrees of freedom. But here's what you're going to do. Notice the 53.58. Let me go over here. Where's my sample size? Okay, here's 32 and here's 54. What you're going to do is you're going to go degrees of freedom for each. That would be n minus 1 is 31. The degrees of freedom, df, for this one is equal to 53. Now, you would go to the table, the R table D, like we did earlier in the semester, and you would only have one sample. So of course, if you go and say, I can find 31, good for you, but you can't find 53. Well, which one do you pick in general? You pick the bigger. That's why they're going, see this, right? Degrees of freedom is, but that's, we're going to go 53, not 53.5, because you can't find that. Okay, so whether we do 53 or 54, this is rounded to 54, you will not find that in your table. It just starts skipping after 40. You remember that. It skips it. Well, all right, fine. I'll just I'll show you. I know you remember that because it's been the whole semester. Okay, I'm looking here. Give me a second. Oh, here it is. Not that one. Here's the table. See, I can find 31, but I don't want 31. I want 53. See, over here, you can see it's 50 to 60. 50 to 60, it jumps. So I'm teaching you, I am training you to pick the closest one throughout the semester. Pick the closest. So I would pick 50. And that would help you find the critical value, by the way. So I'm going back over here. Dog-eared the last page. So I need the critical value based on this. So we're going to use df equals 50, the closest one. And since you've got alpha is equal to 0.05, and it's a, what tail is it? Well, if you look over here, let's see, have we set this thing up yet? It does not. Oh, here it is. We chose this right here. Now, the reason why we chose that, because in the hypothesis test, oh, here it is up here. It's lower. So this is a one tail, but left. One tail left. One tail. So it's a one tail. So I'm going to look in that table again. Go back to the table one more time. So one tail, 0.05. We go down this column until I get to 50. Right there. 1.7, well, excuse me, 1.676. 1676. The critical, I guess we call it T crit, is equal to 1.676. And because it was a less left tail, this has to be negative. Has to be. Now, the only use that this would be is if you do the bell-shaped curve. The only good that the data value and also the critical number is if you did the shading. But if you did the p-value comparison, and p-value here 0.059, so 0.06-ish, 0.06-ish is greater than 0.05-ish. So barely rejecting the null, failing to reject the null, barely. So it's weak evidence. If we did the picture here, you would have found here's 0 here, here's negative 1.676. The data value is here, which is on the right-hand side. This is your data, and the shading was always to the left. So again, to confirm, don't reject at all. And it's very close. So again, weak decision. So here's a statement at the end. At this level, you can't determine whether Professor Sullivan is actually a tougher grader or not. There's not enough evidence to determine that. Okay, that gives you a preview of what we're going to do. I think I have maybe 2 problems to do. And here's the first one. So resting, hey, go back to the pulse rate, resting pulse rates. And then you had non-smokers. Okay, so you're not non-smokers and you got smokers. So that's your 2 samples. So smokers, S-M-O-K-E-R, smokers. Let's make them mu sub 1 grouping just because they're listed first, and non-smokers mu sub 2. So we're wondering if there's enough evidence to see that there's a difference. Difference again. So what we're going to do is one's less than others. Well, let's take a look here what we got. N is equal to 26. Got to be careful here because that's not bigger than 30. Here's the key right here. They're roughly symmetric means approximately normal. That's what they're saying, approximately normal. So even though this is less than 30, somebody had evidence or information that we can go ahead. It's approximately normal. So then we can move forward with even with the 26. So N sub 1 is 26, X bar sub 1 is 80 beats per minute. And little s is equal to 5 beats per minute. N sub 2 was 32. So 32, and its average was 74, and its little standard deviation, so number 2 would be 6. So look at the smokers had, okay, these are smokers down here. This is, excuse me, these are smokers on the top, smokers and non. And so healthier, non-smokers are healthier, so their heart rate should be less. And so this should be greater. So I'm going to do it as H sub naught and H sub A mu sub 1 equals, I'll go back to the equals. And mu sub 1 would be, okay, just look at the numbers, looks bigger than this one. So it looks bigger than this one. So now I'm going to go through the step again. So alpha is not given, so alpha is equal to 0.05 again. We're going to take the degrees of freedom to be the bigger of the two. So df, we're going to take that to be 31. And t crit, since it's a right tail, it'll be positive something, and data will come from the calculator somehow. I'll show you that. And then the p-value come from the calculator again. I'll show you that. Squiggle, p-value. So as you go back over here and you saw how they got this result, I'll zoom in. You can see what we're going to do is use a two sample t-test. That's the one we want, 2 sample t-test. Let's go over here, calculator, find the calculator. go back into stat tests to sample t-test right there. To sample t-test. Enter. We've got statistics, not raw data. So over here, statistics, we're going to type in all the information I have right here. Okay, here we go. Okay, picking the greater than, because that's what we had. Again, just to show you, greater than right there. That's good. Pooled, no. Always say no for the pool. And then calculate. So the data value is 4.15. I suppose, sorry, I put that in the wrong place. So 4.15. I haven't found the crit yet. I think it doesn't matter because that's going to be bigger than any crit I'm going to have, but I'll show you to find the crit. The p-value is significantly small, so 0.0234 and then a 6. That's definitely less than any alpha that you can come up with. So it's going to be a strong reject the null. The critical number, if you're going to draw the picture, which I'm not, the critical number would be the following, looking for it. Okay, 31 and 0.05, so second column, 31. I see 1.696, 1.696, 1.696, 1.696, definitely bigger than that. If you drew your picture, so reject the null. And you'd make a statement like, so since I'm rejecting this, it looks like there's strong evidence, or there's enough evidence, strong because that p-value is extremely small. I'll just say there's evidence to suggest that there is a difference. Matter of fact, it's a positive difference, meaning that the the resting pulse rate is definitely worse for smokers than there is for non-smokers, or the other way. The pulse rate is greater. It's a bigger number, so it's worse. There is a difference in between the smokers and non-smokers. Okay, then there's a section on confidence intervals. Now, if you did confidence intervals right here, all we're going to do is look at all this information, which is a two-sample confidence. Let's see, take a look and see if the confidence intervals are in here. Let's see, hold on a second. Stat, tests, two interval down here, two interval. Let's see if there's a two-sample t interval. Yep. So let's see, is this all the same? It is all the same. Look at that, all the same, all the same, all the same, all the same. Okay, all the same, calculate. And what you have is two numbers. You got 3.11 is less than mu sub 1 minus mu sub 2. And then 8.89 beats per minute. So the difference is a positive difference. That means that's what we're suggesting. The difference is between 3 and 9 beats per minute, somewhere in there. That's the difference. Now, what you're targeting is mu sub 1 minus mu sub 2 is 0. Think about that. This right here is equal to 0. It's because here, if I move this over to the left-hand side, mu sub 1 minus mu sub 2 is 0. Is 0 in here? Of course it's not. And so in a previous chapter, you learned that if the target number that you're trying to show is not in the interval, then you will reject the null. If it's not in here, you reject the null. If the target number is in there, then you don't reject the null. Okay, and the last problem we'll do is we'll put it in list 1 and list 2. Basically, that's what it is. Is there a difference in saturated fat content for the pizzas of the two chains? We're going to find out. Let's see what happens. I'm going to go into here and go list 1, list 2, stat, edit, get rid of all this stuff. And I'm going to put all the information here. So I'll just do the brand D is number 1. Individually, now, if I just looked at the numbers here and down here, boy, this looks like they're all higher. So it looks like there's a difference and this one's higher, but statistically speaking, we'll see if there's enough evidence for that. Go over here, list 2, and that would be brand PJ. And also recognize that sample sizes are less than 30 on both of them. And it doesn't say anything. Let's see if it says anything that's normally distributed. It does not. So what we should do is look at the density plot, which I'm going to do briefly right now for you. So I'm going to go second stat plot. That's turned on. Okay, turned on. This is good. Okay, I'll start with list 1, and then I'll show you how to change this to list 2. So I'm going to go list 1. Everything's set up. I'm going to go into zoom plot, zoom 9. Pretty darn straight, approximately normal. Don't worry about this funny little line. That's because I've got something else from another class in here. Get rid of it. Fine, clear. Okay. Then going back in and checking the other one, you do the same thing here. You just right here, list 1, you make it into a list 2, and this is how you do it. Down here on, at least for the 84, there are numbers 1, 2, and 3 as an example. List 1, list 2, list 3 are in blue. So I'm going to access list 2 with the blue button number 2. And how I access it is I'm going to hit blue second and number 2. And then if you look here, it just changed it to list 2. And then I'll do zoom 9 again, zoom 9. And yeah, it all looks pretty straight, pretty good. So we assume approximately normal. Per density plot. What do we need? All we need is a p-value. Honestly, that's all we really need. So alpha not given. Nope. So 0.05. The p-value. I probably ought to set up the hypothesis test. I really do. So that's mu sub 1 equal mu sub 2, mu sub 1. Okay, this looks like it's going to be higher without even looking at the test, the statistic results. So it looks like it's going to be higher. Okay, fine. You want to know. Okay, let's see. Stat, tests, 1, 2 sample t-test. Oh, we have to do data, raw data. Watch this. Raw data like this. Okay, I'm going to take list 1, list 2. These are the same. Okay, the first one looks higher. So that looks like it's going to be bigger. P-value 1.57. Okay, so this looks higher than this. So p-value apparently looks like it's 1.5. Oh, but look at the E right there again. So that's going to be squiggle, 0.1234 zeros. And then the next number might be a 2. Might be a 2. Oh, that's less than my alpha. So what do? Reject the null. Reject H sub naught. So we throw that away. Yep, looks like there's enough and strong sample evidence to support this claim. So sorry, I changed my mind and I misspelled a word. Is greater than that for something to that effect. Okay, then I think that wraps that up. Should be enough for you to help you get through the rest of the problems in this section. So until next time, have a great day.